Large-scale dose-response screens are used to test efficacy of therapeutic agent for various conditions. We previously proposed a Bayesian inference model called BIDRA for the assessment of dose-response parameters. In the present poster, we quantitatively demonstrate the robustness of BIDRA compared to the standard Labelle approach. We also demonstrate that observed discrepancies between replicated experiments are in part due to the analytical method used to summarize responses set into parameters. Finally, we put BIDRA into perspective with a real-life example. We use 4 data sets, 3 large publicly available data sets for the demonstration of BIDRA's robustness and 1 smaller in-house data set for the real-life analysis example. The 3 large datasets are GCSI, GRAY, and CTR-PV2. Their respective normalized viability responses were obtained through the PharmacoGXR package. The IRIC dataset comprises 63 drugs, 1 reference compound with multiple replicate, and 62 analog compounds. The compounds were tested on 1 leukemic cell line, and the principal aim of this in-house screen is to identify and select analog compounds that are more potent than our reference compound. We use a 4 parameters log logistic model to describe experimental dose-response relationships. For each experiment of gray GCSI and CTR-PV2, we estimated the parameters of that model using the Labelle algorithm. For each experiment of all 4 datasets, we inferred posterior distribution using our BIDRA model. To assess discrepancies, we compared metric of unique replicates, ignoring replicates of more than 2 experiments. The distribution are compared using a quantile-to-quantile approach. We use a standard deviation of viability response to qualify the completeness of a set of responses. Small standard deviation are characteristic of seemingly unresponsive or incomplete responses, and large standard deviation are generally indicative of complete response curves. We quantify the uncertainty of a posterior distribution as the difference between the bounds of its 95% confidence interval, denoted on the poster as delta. We first evaluated the correlation between responsive of shared concentration between pairs of replicates. We found that most pairs shared all concentration and that they have highly similar responses. Based on these results, we concluded that it is reasonable to expect correlation between metrics of pairs of replicates, as these metrics are derived from the observed responses. When comparing BIDRA to the standard Labelle, we observed that both BIDRA's representation have higher correlation than the Labelle estimate, with QQ posteriors having the overall highest correlation coefficient. Single point values, estimate, and median seems to obscure relevant information. Difference between the 2 approaches arises from their handling of incomplete or unresponsive experiments. Labelle estimates are, in some cases, unreliable even when there is convergence. We observed that estimated IC50 are often within the experimental dose range, denoted by the capital D, regardless of the completeness of the response sets or the convergence status. On the other hand, BIDRA generates highly uncertain and mostly unobserved IC50 posterior when the responses are seemingly incomplete or unresponsive. Unreliable IC50 estimates are mostly a consequence of ill-placed HDR. Labelle forces a fit as it is limited to the observed responses. The PF replicates demonstrate the robustness of BIDRA when experiments are incomplete. Both methods return concordant IC50 estimates and posterior distribution. However, Labelle returns arbitrary and discordant HDR, leading to incorrect conclusion. BIDRA's wide HDR posterior mostly align with one another, confirming that both experiments are concordant with highly uncertain posterior distribution. BIDRA seems to be more robust and representative of the experimental context, as it can consider both the observable, experiment responses, and the unobservable through the use of prior distribution. Thus, the probability that a IC50 is unobservable, shown here, is directly related to the completeness of the responses set. This also allows for the correlation of uncertain matrix, as demonstrated here. We can identify many experiments for which BIDRA flag highly uncertain HDR, while Labelle return HDR close to 0. There are numerous experiments for which Labelle and BIDRA leads to different interpretation. For example, AZ and lapinatinib in green and in orange both have wide uncertain posterior distribution, but very different Labelle estimates. Another example would be Labelle forces a sigmoid onto the PF, here, the PF unresponsive response set in purple. It is worth noting that complete response sets, such as gemcitabine in black here, both method leads to similar conclusion. We confirm the validity of all of our observation by considering randomly generated pairs of replicates for 10 repetition. We see that there is overall no or very small correlation between randomly paired data, so the middle panels for each parameters. We observe higher correlation when incomplete data sets are paired because they both rely on the prior. Inversely, we see that randomly paired complete data sets do not correlate. Now that we demonstrated the robustness of BIDRA, let's take a look at how BIDRA can be useful, mainly in the context of selecting compounds. Given the posterior distribution of the 70 unique experiment, we sorted the compounds based on their IC50 rank probabilities. We identified 15 compounds with a high probability, meaning a probability that is smaller or equal to higher or equal to 0.9 of being amongst the most potent, and we defined the most potent as being the first 20 ranks. This is denoted by the red box. We observe that many of these compounds have overlapping IC50 posterior and distinctive HDR posterior. We represented statistical relationship between our top 15 IC50 with a DAG. Here, there exists a path between A and B if and only if A is significantly more potent than B when we compare the posterior distribution. We are thus able to identify 8 analog compounds that are more potent than our reference compound. Finally, we calculated a global probability for each identified analog, giving a set of criteria listed here. We are thus now able to make an informed selection of compound. Thank you for your interest in our work and have a great day.